doing 2.6, which is related rates. Yet again, I have pre-printed us some problems. I know that they might still be a little bit too small. I tried to make them pretty giant font, but I will read them to you as well while we do them. So, let's start with E2. A plane flying horizontally at an altitude of 2 kilometers and a speed of 700 kilometers per hour passes directly over a radar station. Find the rate at which the distance from the plane to the station is increasing when it is 6 kilometers from the station. Alright, so, I think the diagram down here works. Okay, so let's do, we are doing E2. Okay, so it doesn't matter which way you have your plane flying, right? What matters is that it passed over a radar station. So I'm just gonna put a little R there for radar for a second, okay? And so there's a plane, right? And that plane is flying at an altitude. Altitude means directly above, right? Like straight up and down from the ground, at an altitude of 2 kilometers. Okay, and then the plane has passed the radar station. So the plane at this point, and I'm going to have my plane going this way. You could have had your plane going the other way. It really doesn't matter. Also, pardon my inability to draw things. Okay, so we have a plane. Okay, so here's what we know. We know the plane is flying horizontally, right? It's staying at a constant altitude of 2 kilometers, right? And then we have this distance from the radar station to the plane. We can assume that the altitude makes a right angle with the plane because altitude means a vertical line, and the plane is flying horizontally at the same altitude, so we know that that makes a right angle. If you feel more comfortable, you could also do the same exact triangle this way. Like if you like this better, you could have the distance go this way and up, it doesn't matter. Okay, so I know that this value is a constant 2 kilometers, right? I'm going to use this side as P for plane, okay? And I'll use this side as D for distance, which I'll admit is a little bit gutsy because we already have DD, like we have DD dt then, and that's fine. Okay, so here's the issue. We know how fast the plane is flying. When I draw my rates, dp dt, right, the rate at which the plane is changing with respect to time, is 700 kilometers per hour. It's positive because p is getting bigger. It has nothing to do with whether I have my plane flying to the left or to the right. This quantity that I labeled p represents the distance between this radar station and this plane, right? The horizontal distance, not the straight as a crow flies distance. This represents what we can often call the ground distance. So sometimes you'll see it measured this way instead, and they'll use maybe g for ground distance. When we talk about ground distance, we mean like if they were on the same height level, how far apart would they be? So this is the actual distance between them, but the ground distance would be the measurement if you just measured if they were at the same physical height, how far apart would they be? Okay, so ground distance essentially is saying if you pretended the plane was on the ground, how far apart would they be? Okay, so I have a 2 kilometers, a P, and a D, right? And the question that they ask is, how fast is the distance, at what rate is the distance from the plane to the station changing when the plane is 6 kilometers from the station? So what they seem to want is dd dt, right, the rate that this distance is changing, at the moment when d is 6 kilometers, okay? They want to know, at the moment when the plane is 6 kilometers away, how fast is that rate d changing? Okay, so knowing all that, that's our diagram and our rate, right? That's the dr of Dreadsaw, right? Now I need an equation that relates them. Again, you will be shocked how many times that equation is Pythagorean theorem. The odds are very high if it's a right triangle that you're looking at Pythagorean theorem, and here we definitely are, right? 2 squared plus p squared equals d squared. So 2 squared plus p squared equals d squared. When I differentiate with respect to time, the 2 squared differentiates to 0 because it's a 4 and derivative of a constant is 0, plus 2p dp dt equals 2d dd dt. Now, I know I want this, so if you want to go ahead and solve for that, you can. You certainly don't have to. If you solve for that, you're going to get 2p dp dt over 2d, I'd probably suggest you cancel the 2's, equals dd dt. So this is the equation I need to use, right? This guy right here. So when I substitute in, I'm substituting in when d is 6. Well, the problem is, if you look at when d is 6, that is very much not a Pythagorean triple. You're going to have to find the value of p. So 2 squared plus p squared equals 6 squared. 4 plus p squared equals 36. P squared is a 32. My p is a root 32. Now, if you're that person who sees that this is a 16 and a 2, you could make this a 4 root 2. Either is okay. All right, so Doesn't matter which of those two you pick, right? How much you simplify. Now, again, we simplify selfishly at this point in math. So if you're looking at multiple choice answers and there's no square root of 32s, well, then maybe you need to simplify. So now when I go to substitute in, I say, okay, cool. So my dt is p, which we established is either a root 32 or a 4 root 2. I don't care which one you pick. dp dt, which we said was a 700, right, over d, which is a 6. I know that the distance is measured in kilometers, so dd would be measured in kilometers. dt was measured in hours, right, so kilometers per hour. You could probably leave your answer like that. I would suggest that it's more likely that you're going to see this as the 4 times the 700 times the root 2 all over a 6, and that they're probably going to cancel a 2 out of that. So what you're probably going to see is 1400 root 2 all over 3 kilometers per hour. Now, that said, it was a right answer up here, right? As long as you have the units, it was a right answer the whole way down here, right? Again, notice that most of the time when your answer comes out positive, you don't have to sweat it too much about whether you have to check if the direction mattered, or if the question was worded in some sort of a funky way. Here, I want to know how fast the distance is changing. I'm assuming that this is a non-calculator problem. If it's a calculator problem, you can also just totally get the decimal value, and that's dope and totally fine. If you get a decimal value, you should round or truncate to 3 places, right? But there's our answer. So I'm going to erase this, and then I'm going to read you P2, and then after I read you P2, you can pause me. If P2 is big enough that you can comfortably read it, you can also pause me right now. But I'm not sure what everybody's level of needing glasses and or like screen abilities are, so I'm going to read it. I know I can't see much without mine. So, P2. A ship is 400 miles directly south of Tahiti and is sailing south at 20 miles per hour. Another ship is 300 miles east of Tahiti and is sailing west at 15 miles per hour. At what rate is the distance between the ships changing? Cool. So if you are fine with that and you don't need to listen to me, go ahead and hit pause. All right. So in general, you don't have to do this, but it's way easier if north is up on your paper. Like, that's just generally the accepted approach, is to have north be up. So I always use never eat slimy worms. Some people use never eat soggy waffles, never eat sour watermelon. I don't know. I always say slimy worms. So, all right. So here's what I know. Tahiti seems to be the middle of this problem. So I have a ship sailing south of Tahiti, and I have a ship sailing west, but it's starting east of Tahiti. Okay, so here's what we've got. Here's Tahiti. I have a ship that is 400 miles south of Tahiti. Okay, so it's 400 miles already. I'm not going to label that, though, because it is sailing from here. It is sailing south. Okay, so I'm going to call this ship A. Ship A is sailing south, and so actually let's just call this, give me a sec. I'm going to call this one, I'm going to call this ship A, and I'm going to call another ship, we'll call this ship B, right? Okay, so here's what I know. I know that so I'm going to call this A for ship A, and I know that dA dt, right, the rate at which that A is changing, is 20 miles per hour. 20 miles per hour. Now, notice that the 20 is positive. The reason it's positive is because A is physically getting longer. The ship is south of Tahiti, and it is sailing farther south, right? So that value is positive, A is getting bigger. But there's another ship, right? There's another ship that is starting 300 miles east of Tahiti, right? And it is sailing west, which means it's sailing towards Tahiti, right? Sailing this way. So I'm going to call this measurement B. What that means is that dB dt is a negative 15 miles per hour, right? The reason it's negative is because B is getting physically smaller, right? B is the measurement from here to here. Well, as the ship moves, B gets smaller, so dB dt is negative. Now, the distance between them, I'm going to use D, so it seems to me that what I want is dd dt at the moment that they are describing here. And the moment they are describing here is when A is 400 miles and B is 300 miles, right? The reason I couldn't put the 300 and the 400 on my diagram is because the 300 and 400 are changing. Sure, at the moment when the instant that this picture was taken, A is 400 and B is 300, but because the two ships are moving, I can't leave those numbers on my diagram, right? So this is my diagram with my rates. Okay. Now I need an equation. Well, shockingly, it is Pythagorean theorem. So a squared plus b squared equals d squared, right? So when I differentiate, now this is tricky because none of these are constant, right? So I'm going to get 2a dA dt plus 2b dB dt equals 2d dd dt. Now I want dd dt, so I could just divide the whole thing by 2d if I want. So if I want, I can make this 2a dA dt plus 2b dB dt all over a 2d, and again, I'd probably cancel those 2's, but it's up to you, equals dd dt, right? Because I could factor a 2 out of the top and cancel them. I can only do that because they literally all have a 2 that I could factor out. Now, I want to substitute specific stuff in. Well, here's the fun thing. I know at this moment that I have a 400 and a 300 and d. Well, remember we talked about Pythagorean triples. There was a 3, 4, 5. That includes all multiples of 3, 4, and 5. So if this is 300 and 400, then the hypotenuse is 500. Now, if you don't see that, you are welcome to go ahead and do Pythagorean theorem to get that value. But again, the AP is counting on the fact that you can spot a 3, 4, 5 right triangle. So when I substitute in, my A was 400 times a 20, plus my B was 300 times a negative 15, all over a 500. And then I need to clean that up, right? Honestly, if I were you, I might just go ahead and cancel some 100s to make your life a lot easier, right? If you factor out 100, right, from the top and bottom, you end up getting that this is a 4 times 20, which is 80. And then this is a 3 times a negative 15, which is a negative 45. And on the bottom, you just get 5. So again, the math gets a lot easier. You get 35 over 5, which is 7. So your answer is 7 miles per hour. Right? And that makes sense because remember, dd dt, if you're not sure what the units are, I am no science teacher. I'm really bad at keeping the units the entire time. A better science, like a science teacher would have told you that you should have, when you plugged in A, you should have had miles. And when you plugged in dA dt, you should have had miles per hour and same thing. I'm just totally not that person, just being honest. My take is that if I know what answer I'm looking for and I know what that answer is measured in, then I really don't have to keep the units the whole time. Again, I'm a terrible person as a science teacher, so that's why I don't teach science. So I know that dd means the change in the distance. Change in distance is in miles, and dt is change in the time. So change in time is in hours, hence miles over hours or miles per hour. Okay? Okay, I'm going to erase and we're going to go ahead and do an E3 and a P3. Again, we have a lot of practice problems in this particular section. All right, E3, P3, here we come. All right, so E3 and P3 are going to deal with angles. Unless angles are specified, you should assume that everything is in radians, okay? If an angle is specified as degrees, then you're working with degrees, but the default assumption on AP Calc is that you are always talking about radians. All right, so let's talk about E3 first. E3, a plane flying at an altitude of 1 mile is 2 miles distant from an observer, measured along the ground. Now that's important because they're saying that is ground distance, and flying directly away from the observer at 400 miles per hour. How fast is the angle of elevation changing? Okay, so I've got an observer. We always assume that observers have no height, which I know is like weird and boring and crazy and not right, but it is what it is. Okay, so the plane is flying away from the observer. So this is my plane. Right, okay, there's my plane. Here's what I know. Number one, I know that it's flying at an altitude of 1 mile. I can put that on there because the altitude is constant, right? Number two, I know that the plane is moving, so I need a variable for this. I'm just going to use x for the plane this time. There's no way this is a constant, even though they do mention how far the observer is from the plane. There's no way it's a constant because then the plane would not be flying, it would fall because planes have to be moving to fly. Lift and everything. So what I do know is that I know how fast the plane is flying. It's dx dt, because I used x for the plane this time, and I know it's a positive 400 miles per hour. It is positive because as the plane flies, x will physically get longer, right? Because the plane is moving away from the observer. If the plane were moving towards the observer, then it would be a negative 400. We know that this creates a triangle, right? And we are asked how fast the angle of elevation is changing. Now, the thing to keep in mind, angle of elevation means this angle right here, right? But it also means this angle, because the angle of elevation that the person is looking... So my point is that you could have either measured this x along the ground and this 1 mile over here, right? Or you could measure it the other way. It doesn't matter which of these triangles you use, okay? The angle of elevation from the person is the same as the angle of declination from the airplane, right? So the angle at which I look up at you is the same as the angle at which you look down at me. They are alternate interior angles if you want me to go old school geometry on you. Okay, so here's my diagram. What I seem to want, right? What I seem to want is d theta dt, because I want to know how the angle is changing at the moment when x equals 2 miles. Because they did mention that along the ground, the person is 2 miles from the plane. But again, that can't be on my diagram because that's not a constant, right? If that were a constant, it would mean the plane wasn't moving, and that's not how planes work, right? Okay, and we were also told the plane is moving. Okay, so now we get a little bit more difficult because now I need an equation that relates them. So I'm looking at a right triangle that is talking about angles and sides. That's SOHCAHTOA, right? So we're going back to old school trig. So I look and I recognize that the 1 mile is the side opposite the theta, and the x is the side adjacent. And that's true whether you use this theta or this theta, it's the same idea. So I realize that I'm looking at tangent, right? Because as soon as you see that it's an angle, right? You see that it's an angle, your brain should be like, oh, SOHCAHTOA, right? And we want tangent, which is opposite over adjacent. The only time you're really going to see that it's going to be sine or cosine is if you know the hypotenuse. So you'll sometimes see it as sine or cosine if you're talking about, instead of an airplane, if this were a kite, because kites fly on strings, so you know the length of the string. But most of the time it's not going to be sine or cosine, it'll be tangent. So the relationship I want is that tangent of theta is the opposite over the adjacent, so 1 over x, right? Or if you prefer, you could flip it up and make it an x the negative first. It doesn't matter. Okay. So that's my relationship that I want. Or you could, so the other option is if you prefer to have the x on the top, you could make this the cotangent and make it an x over 1. That would also work fine, right? Either of these is going to get you to the same spot. I promise it really doesn't matter. I think most of us would probably have done this because most of us feel more comfortable with the SOHCAHTOA stuff. So now I need to derive with respect to time, right? I'm going to differentiate with respect to time. So if I were you, I would rewrite this as an x the negative first to make it a nice easy chain rule. You don't have to, but I would suggest that that's the easiest option. So now when I differentiate, the derivative of tangent of theta is secant squared of theta. But I just differentiated something that wasn't t with respect to time, so I need to do d theta dt. On the other side, I'm going to get a negative x the negative second dx dt, right? So it seems to me that I get a secant squared theta d theta dt equals a negative 1 over x squared dx dt. Now remember, I'm trying to find this. So there's a couple different ways to deal with this. One thing worth recognizing is that secant squared is the same as a 1 over a cosine squared. So you could multiply that cosine squared over, and you're going to get d theta dt equals negative 1 over x squared times dx dt times the cosine squared of theta, right? I get that you're hating this, by the way, in case, like, you don't even have to be in the same room as me, and I can tell you hate this. So now I need to substitute in. Well, let's think about what we know. When we go to substitute, we are looking at the exact moment when this is a 1, this is a 2, and here's my theta. I don't know the hypotenuse. You're not going to solve for theta. That would be a calculator problem. What you are going to do is find the missing side using Pythagorean theorem. So the missing side, right, is 1 squared plus 2 squared. Right, so 1 plus 4 in a square root, so this is a root 5. Now, here's why that's useful. You know what the cosine of theta is because it's called SOHCAHTOA for a reason. It's the adjacent over the hypotenuse. So your cosine is the 2 on top of the root 5, which means that your cosine squared of theta is a 4 on top of a 5. So now when you go to plug in, you're going to get that your d theta dt is a negative 1 over x squared, but we know in this case I think that x was a 2, right? That's what we figured out. So negative 1 over 4. dx dt was the 400 miles, right? And then times a 4 over 5, right? So I can cancel the 4 with the 400 and just get a 100, right? Or the 4 over here, which is probably easier, right? Either way, I end up with a negative 400 over 5. Which would be a negative 80, right? So my answer is a negative 80, and then theta is measured in radians, right? And time is measured in hours, right? And they said how fast is it changing, so you want to keep the negative, right? Because the negative indicates that the angle is getting smaller. So you do want to answer with the negative. If they said how fast is the angle decreasing, well, then you wouldn't need the negative, because the negative is telling you the angle is getting smaller. It also makes sense that the angle is getting smaller, because if you picture looking at something really tall very close to you, you have to look up, right? If I stand right next to City Hall and I try to look up, I have to look almost vertically, right? But if I'm standing up by school and I look at City Hall all the way from up way on North Broad, I barely have to elevate my eyes at all to see City Hall, right? So it makes sense that that angle is getting smaller, and it is getting smaller at a rate of negative 80 radians per hour, okay? So I'm going to erase this, and then I'm going to read you P3, and you give it a try. Hint, hint, wink, wink, nod, nod. It's probably more angles because it says angles. Okay. P3. A rocket rising vertically is tracked by a radar station that is on the ground 0.5 miles from the launch pad. At what rate is the elevation angle changing when the rocket is 300 feet up and rising vertically at 500 feet per second? Now, there is a little tricky thing that happens here, just so you know. Miles, and everywhere else it's feet. So you're going to have to convert miles to feet. So just notice that that's a trap, right? It's a trap that they didn't convert miles to feet. 1 mile is 5,280 feet, which is a good thing to know, just because it comes up a lot in science and math. So anyway, you go ahead and try P3. Pause me if you want. I'm going to do it now. So P3. Cool. Here's what we've got. We've got the ground. I've got a radar station here, and there's a rocket. I don't know what the rocket's going to like. Make it look like the thing with the, like, should I make it look like a spaceship? I don't know. It doesn't. It's like, woo. Okay, great. Okay, so so a rocket is rising vertically, and it's tracked by a radar station on the ground that is 0.5 miles away, right? So half of this should be 2,640. So 2,640 feet. Okay. Again, we can assume that ground is horizontal unless we're told otherwise. That is a stationary thing, like the rocket's going straight up, so the rocket is always going to be that far away on the ground, right? You're looking up at the rocket. They ask about the angle of elevation, which is here. We know the rocket is changing. Some of these R for rocket. Maybe I shouldn't have, because of, we'll use H for height of rocket, because I did say that it was a radar station. So H for the height of the rocket, and we're going to say that dH dt is, the rocket is rising 500 feet per second. Okay, cool. And they say, so what we want, right, so what we seem to want in this problem is d theta dt, because they ask how fast is the angle of elevation changing, at the moment when h is 3,000 feet. Okay, so that's what we seem to want. So there's my diagram and my rate, right? Yet again, I'm looking at TOA, right? I see that it involves an angle, so that's definitely SOHCAHTOA. I know the opposite side, and I know the adjacent side, so that's definitely TOA. So when I make my equation, I'm going to get tangent of theta equals the opposite, which is h, on top of the 2640, right? So when I differentiate, remember that this, by the way, is just the same as this coefficient, the 1 over the 2640 times h, right? So we already saw that the derivative of tangent was secant squared theta d theta dt. On the other side, I'm going to get a 1 over 2640 times dh dt, right? This is what I want, but again, we already saw in the last problem that secant squared is the same as a 1 over a cosine squared. So I can just solve by multiplying the cosine squared over. So I'm going to get d theta dt equals a 1 over a 2640 times whatever dh dt is times cosine squared, right? So now when I go to substitute my specific stuff in, I'm substituting at the moment when this is 3,000, this is a 2640, and this is a question mark that I'm going to have to find, right? Because in order to find cosine, I'm going to need to find that value. Now I'm going to own up to the fact that this is probably not a non-calculator problem with numbers this big. So I'm just going to own it and say, hey, go ahead and use your calculator. So I'm going to find this mystery side. I'm just going to call this side x because I didn't have an x, right? So I know that x squared is going to be the 2640 squared plus the 3,000 squared, and I'm definitely not doing those in my head, and that is not a level of expectation that the AP would have either. So don't panic if that's where you're at. Okay, so I get a ridiculous number, right? I'm going to get that x is the square root of 1599600, which is insane. 1599600, right? Nobody's going to expect to do that by hand. All right, and you're going to get, this is a crazy number. So I'm going to go ahead and rule that this is probably a calculator problem, because yikes, right? You can try and clean this up if you want, but it's pretty disgusting. So I'm going to go ahead and rule this is probably a calculator problem. I'm going to go ahead and store that in my calculator as alpha A. So to do that, I hit stow and then alpha A. All right, so I'm going to go ahead and call that A. So when I go to plug in, I'm going to get that my d theta dt is 1 over 2640 times a 500 times my cosine is going to be the 2640 over a quantity squared, right? So that's completely disgusting. One of the 2640s cancels, if that makes you feel any better, right? So you could, if you really wanted, make this a 500 times a 2640, one of those two cancels, over an a squared. But I don't know why that would help, because it just doesn't really seem to help much. So if I were you, I'd just go ahead and type. So you're going to get, I'm going to type in 1 divided by 2640, right? And then a 500, and then a 2640 divided by a quantity squared, right? So that's what I typed into my calculator. And then I'm going to hit enter. And I'm going to get this completely disgusting 0.08, either 2 or 3, depending on if you round or truncate. And again, it's going to be radians per second, because I look at what the unit of the angle is, which is radians unless I'm told otherwise, and I look at the unit of the time that's in here, and it's seconds. So there's my answer. There's the in dread sum. Okay? Again, I get that these are not easy problems. You'll know very clearly on an AP and also generally on our homeworks whether something is calculator or not. Honestly, I didn't realize this one was going to need the calculator until I had to do those numbers and was like, nah, bro, that's not a thing I'm going to do. So, anyway, there you have it.